the second page of the worksheet, we have more problems about when relations are functions. So we approach these the same way that we did the other ones, where we want to just give ourselves a little bit of information about what the relation R actually is doing, and we can do that by just writing out some of the pairs that are described in the set. So in this relation, for every input element, AB, we want to include that pair in our relation if A plus 2B is equal to 1. So for example, if A is 1, if the first coordinate is 1, then in order for this equation to be true, B would have to be 0. So 1 comma 0 is a pair AB that satisfies 1 plus twice 0 equals 1. Here the A and B come from integers, so negative numbers are okay, so we could have negative 1 here. If A is negative 1, then the only way for this equation to work is if B is positive 1. So negative 1 plus 2 times 1 is 1. That's true. And so we can fill in a few examples like this, but one thing we'll notice is that we can't find the second coordinate if we start off with an even number. Think about it. If A is 0, then in order for this equation to be true, 2B would have to be 1. But the B elements have to come from the integers. So there's no integer B such that 2B equals 1. So there isn't going to be a pair like this. So the pairs we're going to get are just going to be ones that have the A coordinate being an odd number. So if A is 3, then B could be negative 1, and that's okay. We have 3 plus negative 2 equals 1. If A is negative 3, then B is 2, and so forth. But right away we've discovered that we're missing entries. So a number like 0 is an okay domain element, but it is not paired with anything in the codomain. And so this is not a function for that reason. Let's abbreviate that, not fun. The last part here is to go back and think about whether the R inverse in each of these cases is actually a function. And so to do that, we have to revisit each of the ones that we had before. And we can write out a few terms for each of these relations from 1, 2, or 3. So take a second. Remember, R inverse means to just reverse the order of the pair for each of the ordered pairs. So I'll do the third one since we still have it on the screen, and then I'll pause the video while I fill in the other ones, and you can do the same. So for the third one, R inverse is got 0, 1, because that's what we get by reversing the coordinates in this pair. 1, negative 1. That's reversing the second pair. Negative 1, 3. To negative 3. So that's the reverse of all the pairs that I've shown in that example. So I'll pause the video here if you want to write down the reverses of the pairs from the two on the previous page. Okay, so hopefully your pairs look something like this. I didn't write down all of them. I want to give myself enough room to write over here. But I can see right away that in this first example, I do have a problem with, where's that? I do have a problem with the input of 5. The input 5 has multiple outputs, and so this R inverse is not a function because we don't have just one output for the input 5. However, both of these last two examples, you can even see from the way I've written them that every natural number in the first coordinate, 0, 1, 2, 3, 4, each of those natural numbers has an output, has only one output, and those outputs are in the set of integers. So this is a function, and in fact both of these are going to do this. Each of these is a function. The first is a function from the natural numbers to the integers, and the second one is a function from the integers to the integers. And on the solutions, it will sort of explain why that works. It's just because the formula, when you write it, for every input, you can just look at the formula and see that you will get an output in the correct set. So now moving down to the stuff from 4.6, which we'll finish on Monday. The first part is just using the floor and ceiling function, and so this is just a matter of getting used to the notation. So if you're not sure, I would just Google floor and ceiling functions to look for more examples, and you can see my solutions on the third and fourth page of this handout. So I won't bother doing these here. This question, how many numbers in a set are divisible by 21? This is an application of the floor function. This is the floor of the calculation 2014 divided by 21. So if you do that calculation and take the floor of that answer, that will be the correct answer to that question. And that's related to the idea of quotient that we'll discuss in class on Monday. For the numbers divisible by 3 or 7, this is the inclusion-exclusion principle that we talked about back in section 3.1. This is the number of numbers in that set divisible by 3. This is the number of numbers in that set that are divisible by 7. And just adding those two together overcounts, because it counts all the multiples of 21 both times. Anything that's divisible by 21 is going to get counted here and here. So to correct for that, we subtract off the number of multiples of 21, which is the calculation in the previous problem. The problems that are more difficult are the ones that involve logarithms. And so we learned that the answer to this question has to do with the logarithm of 117 factorial, which your calculator will not be happy with. But because the logarithm of a product is the sum of the logs, this is the same thing as summing the log of k for values of k ranging from 1 to 117. And that's something that you can figure out using a calculator function that's given on the slides for the section, or you could do it in Excel or something like that. But once you have that answer, then you're just going to take the floor of that and do that same kind of calculation that we did before. That one is not a very practical test question because it requires you know something about technology, a calculator, something. This question, number 5, on the other hand, is not a bad test question because all you have to have is a scientific calculator and know the rules of logarithms. So this logarithm is just the sum of the two logarithms that make up the parts of the product. So again, the log of a product is the sum of the logs. So I can break up, because this is a product in this problem, then the log of that product is the sum of the two logs. When I have the log of an exponential, I can pull that exponent outside of the log. In both cases. So all my calculator really has to be able to do is 117 times the log of 17 plus 17 times the log of 117. All of those are easy calculations, and from that answer we can determine the number of digits that this number has. The stuff from section 4.6 we will discuss again on Monday before we have our review on Wednesday and our exam on Thursday.